Hello, my dear students, and welcome back. I know your exams are just around the corner, and the tension must be building up, है ना? But don't you worry. As always, your sir is here to help you out. Today, we're going to tackle Chapter 5, Magnetism and Matter.
Yes, I know what you're thinking. So many of you have told me, Sir, this chapter is a bit confusing. All these new terms, all these concepts. The questions seem so simple, but they can be really tricky, isn't it? And that pressure to remember everything for the boards. I know, it's real.
But you really don't have to worry one bit. We are going to break it all down, make it super simple, and I promise you by the end of this short explainer, you're going to feel so much more confident. Okay? So, just take a deep breath, and let's begin.
Right, let's start at the very beginning. Back to basics with the simple bar magnet. After this, we'll look at the one big rule that explains everything. That's Gauss's law. Then we'll see how different materials behave magnetically. And we'll wrap it all up by solving a really important exam question. Ready? Cello.
You've all done this in the lab, right? You take a bar magnet, put a sheet of paper on top, and sprinkle some iron filings, and poof, this beautiful pattern just appears. This pattern is literally showing us that invisible field of influence around the magnet, its magnetic field. And you want to know the best part? This pattern looks exactly like the electric field of an electric dipole, which you already mastered back in Chapter 1.
Now these lines, they have some really important properties. Beta, please pay attention here. These are favorite questions for 1-mark MCQs. First, they always form closed loops. They don't start or end anywhere. They just loop around. Second, they never ever cross each other. Why? Well, think about it. If they crossed, it would mean the magnetic field has two directions at the same point, and that's just impossible. And remember, where the lines are all crowded together, the field is strong. Where they're spread out, the field is weak. Simple.
And here you can see that connection I was talking about. It's so cool. A bar magnet with its north and south pole is a perfect twin to an electric dipole with its positive and negative charge. Even the formulas for the magnetic field, B, look a lot like the formulas for the electric field, E. So you see, if you understand one, you pretty much already understand the other. Physics is beautiful like that.
Okay, let's build on this idea and get to the single most fundamental rule in all of magnetism. This one law explains something really strange but really important about magnets. I'm talking about the famous Gauss's law for magnetism. Now, the law itself sounds very technical, doesn't it? Net magnetic flux is zero. But the idea is actually incredibly simple. It just means that if you imagine any closed box or bubble around a magnet, the number of magnetic field lines going into that box is always exactly equal to the number of lines coming out of it. Whatever goes in must come out, period.
So, what's the big deal? What does this law really tell us? It tells us something profound. It's the mathematical proof that you can never, ever find a north pole all by itself or a south pole all by itself. They always come in pairs. And this is the biggest difference between electricity and magnetism. We can have a positive charge alone, right? Or a negative charge. But we can never have an isolated north or south magnetic charge. These things, called magnetic monopoles, they just don't exist. All right, so we get how magnets work, but why is a piece of iron so powerfully attracted to a magnet while a piece of wood or plastic just doesn't care at all? Well, the answer is all about how different materials react when they're placed in a magnetic field. Let's really think about this for a second. It's a great question. It's not just that wood isn't attracted. Some materials, like copper, are actually pushed away. They're repelled by a magnet, just a tiny bit. How is that even possible? Well, it's because we can basically sort all materials into 3 different teams.
Bachcho, please take a screenshot of this slide right now. This table is so important for your board exams. I can almost guarantee a question on this will come. So, we have 3 types. First, diamagnetic. Just think, dia means opposite. These materials are weakly repelled by magnets. Their susceptibility, which is just a number that tells us how magnetic they can get, is small and negative. Think of copper or water. Second, paramagnetic. Para means alongside, so they are weakly attracted. Their susceptibility is small and positive, like aluminium. And finally, we have the superstars, ferromagnetic. Ferro comes from ferrum, which means iron. These are strongly attracted with a big positive susceptibility. And of course, the best example is iron itself.
And this picture from your textbook shows it perfectly. Just look at the diamagnetic material on the left. See how the magnetic field lines are avoiding it? They're being pushed away. Now look at the paramagnetic one on the right. The lines actually prefer to go through it. They're getting pulled in just a little bit. It's a great visual way to remember the difference.
So what makes ferromagnetic materials so special, so strong? The secret is something called domains. Imagine a piece of iron is made up of millions of tiny little regions, and each region is like a tiny magnet itself. Now, normally they're all pointing in random directions, so their effects just cancel out. But the moment you bring a big magnet nearby, bam, all these domains snap into alignment, all pointing the same way, creating one super strong magnetic effect. And for materials like iron, they even stay aligned after you take the big magnet away. And that, my friends, is how you make a permanent magnet.
And here is a super cool fact for you. There's a special type of material called a superconductor. These are like the ultimate diamagnets. They repel magnetic fields perfectly. I'm sure you've seen those viral YouTube shorts or Instagram reels, the ones with a small magnet floating in midair above a black disk. That's this. It's called the Meissner effect, and it's the technology behind those incredibly fast maglev trains. That's physics in action for you.
Chalo, enough theory now. Let's put our knowledge to the test. We're going to solve a very, very popular conceptual question that comes up all the time in exams. This will make sure you've understood everything perfectly.
So here it is, straight from example 5.1 in your textbook. What happens if you take a bar magnet and you cut it into two pieces? Just take a second and think about it. What do you get?
Well, it doesn't matter how you cut it. Whether you cut it across its length, like you're chopping a carrot, or you slice it down the middle along its length, like splitting a piece of bamboo, the result is exactly the same. In both cases, you just get two new, complete, but slightly weaker magnets. Each new piece will instantly have its own north and its own south pole.
So, what's the crucial point here? This simple experiment proves what Gauss's law told us in theory. No matter how many times you cut a magnet, no matter how small the pieces get, you can never isolate a single north pole or a single south pole. You just can't get a monopole. You always end up with smaller and smaller dipoles. This is a fundamental truth of our universe.
And that's it. We've covered the most important parts of this chapter. Okay, my champions, let's just do a super quick final revision of the key points you absolutely have to remember for your exam.
So just remember this. Magnets are always dipoles. You can't separate the poles. Their field lines are always closed loops. Gauss's law is simple. Net magnetic flux through a closed surface is always zero. Materials are sorted into dia, para, or ferromagnetic, and that super strong magnetism in ferromagnets, it's all because of tiny domains lining up together. Got it? Perfect.
Before we finish, here's a little something for you to think about. Just look around you right now. Can you think of one device, just one thing that you use every single day that wouldn't work at all without the principles of magnetism we just talked about? There are so many. Let me know what you think of in the comments below. All the very best for your preparation, my dear students. Study well, stay calm, and you are going to do wonderfully. God bless you.